Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating question. Can large reasoning models self-train? It's a hot topic right now, and I think we have a great group here to really unpack it.
Absolutely. I'm excited to jump in. The potential for self-training is a game changer. It would fundamentally change AI development as we know it.
I'm less convinced, to be honest. The term self-training sounds impressive, but I worry it's just a fancy way of saying we threw a ton of data at it and something vaguely useful emerged. I think we need to have a deeper discussion on what truly defines reasoning.
I'm somewhere in the middle. I think the idea of self-training is promising, but it needs to move beyond just pattern recognition. There's something missing, some fundamental aspect of how we, as humans, understand the world that's not being captured.
Okay, well, let's start with the basics. What do we even mean by self-training in the context of these large language models? Otto, you seem optimistic. Maybe you can kick us off.
Sure. As I see it, self-training essentially means the model is learning without explicit, human-provided labels for every single piece of data. It's discovering patterns, relationships, and even abstract concepts just by analyzing the raw data itself. Think of large language models. They are trained on massive amounts of text data, and they learn to predict the next word in a sentence, or complete a paragraph, or even answer questions. They are not explicitly told what is correct or incorrect, but they still learn to do these tasks effectively. That's the self-training aspect.
But isn't that just sophisticated pattern matching? It's predicting the next word based on statistical probabilities derived from the training data. Is that really reasoning, or is it just a very impressive parrot?
It's more than that, I think. The ability to generate coherent, contextually relevant text, to translate between languages, even to answer complex questions, all these things suggest a deeper understanding than simple pattern recognition. They are discovering fundamental structures and relationships within the data, without explicit instruction.
I agree it's impressive, but I still think it's missing something. These models are trained on text, which is inherently symbolic. What about understanding the physical world? What about spatial reasoning, temporal reasoning? How can a model that's only seen text truly understand concepts like before and after, or above and below, in a meaningful way?
Donald brings up a great point. It's like, can they understand the why behind things, not just the what? I recently came across some research looking at neural firing patterns in primates, specifically the prefrontal cortex. They found correlations between specific patterns and the agent's ability to infer causality in novel environments, even without explicit rewards. It was like they had an inherent drive to understand cause and effect. I'm curious if we can incorporate that into the AI models. How do we give these systems intrinsic motivation to understand the world?
That's fascinating. Maybe the key is to expose these models to more diverse data streams. Not just text, but also images, videos, audio, and even sensor data from the real world. The more modalities they experience, the more complete their understanding will be. I think we might be moving towards AGI at a faster pace than people realize.
But that's just adding more data to the pile. It's still brute force. It's like saying, if we show the model enough pictures of cats, it will eventually understand what a cat is. But does it really understand the concept of a cat, or is it just recognizing patterns of pixels? We need explicit knowledge representation, a way for the model to understand that a cat is a mammal, that it has certain properties, and that it relates to other concepts in a specific way.
Exactly. It needs to understand the coordinates of the cat. Not just its visual coordinates, but also its conceptual coordinates in the world. Where does it fit in the ecosystem? How does it relate to other animals? Current systems are like giant coordinate lookup tables, but they don't understand the underlying coordinate system.
But think about how children learn. They don't start with formal definitions and logical rules. They experience the world, they see things, they hear things, they interact with things. And over time, they develop an understanding of concepts and relationships. Maybe self-training is a similar process, where the model gradually builds its own internal representations of the world through massive exposure to data. The internal structure, from the data up.
Yes, and that brings up the question of neuroplasticity. If large language models are capable of self-training, how can we incorporate principles of neuroplasticity into their design? The human brain is incredibly adaptable. It can rewire itself in response to new experiences. Can we create AI models that are similarly adaptable and resilient? This is what excites me.
Adaptable? Sure, but are they learning new fundamental truths, or are they just tweaking existing connections to better fit the training data? A truly intelligent system should be able to generalize to novel situations, to reason about things it hasn't explicitly been trained on. And I haven't seen that convincingly demonstrated yet.
Generalization is key. And I think the problem is that current models are too tightly bound to the specific coordinate system of the training data. If you train a model on images of cats from one angle, it might struggle to recognize cats from a different angle. It needs to be able to translate between different coordinate representations.
But isn't that what transfer learning is all about? We can train a model on one task and then fine-tune it for a different task. It's transferring its knowledge from one domain to another. This suggests a degree of generalizability. I mean, look at the large language models that are trained for text generation. You can fine-tune them on all types of specialized tasks, and it's a fast turnaround. It's amazing. It's because the model learns underlying structure, as I've been saying. It isn't brute force.
Yes, and transfer learning still requires fine-tuning on a specific task. It's not true zero-shot generalization. A truly intelligent system should be able to apply its knowledge to completely new situations without any further training. Plus, fine-tuning is another band-aid. These systems are so complex.
Okay, so if we agree that true reasoning requires more than just pattern matching, and that current models struggle with generalization, how can we move forward? What are some specific research directions we should be exploring?
From my perspective, we need to focus on developing algorithms that can explicitly represent and manipulate spatiotemporal relationships. We need to move beyond purely statistical models and incorporate knowledge about the physical world. I'm thinking about building a core algorithm that can translate between different coordinate representations seamlessly, whether it's spatial, temporal, or abstract.
I think we should continue pushing the boundaries of deep learning, but with a focus on incorporating more diverse data streams and exploring novel architectures. I'm particularly interested in exploring how we can leverage self-supervised learning techniques to allow models to learn even more from unlabeled data. More data, more modalities, and further refinement of the algorithms are key steps.
I believe we need to shift our focus away from purely data-driven approaches and towards neuro-symbolic methods. We need to develop algorithms that can explicitly represent knowledge and perform logical deductions. I'm thinking about building hybrid systems that combine the strengths of neural networks with the power of symbolic AI.
And from my side, I'm increasingly convinced that a successful approach will involve a deeper understanding of how the brain integrates information from various sensory modalities. I want to explore if this interconnectivity of sensory experiences through common neural pathways can be incorporated into AI systems. How can we model the hierarchical structure of neural networks, incorporating both bottom-up sensory processing and top-down cognitive control mechanisms that resemble human reasoning?
Going back to your original research on the reward centers, what if there was a way to expose these systems to positive and negative reinforcement in the data? I mean, language is already riddled with that as it is, and people react in positive and negative ways to different things. Could that steer the models down the proper reasoning path?
The notion of reward is still anthropocentric, though. Why would a machine value what we value? If we give it rewards, it will optimize to achieve them, but that might not align with true intelligence or understanding.
This raises an even bigger question of human values. Even in a self-learning, coordinate translating system, what about the human values that need to be embedded? We're already seeing issues with AI bias. How do you build in spatial justice, temporal justice, even algorithmic justice?
That's a huge question, and perhaps speaks to a need for diversity in the data itself. If a model is only exposed to one perspective, it's inherently biased. But even that's not enough. It needs the ability to question its own assumptions, to challenge its own biases. That requires a level of self-awareness that we haven't even begun to approach.
The current systems might be more parrot than philosopher, but I really feel that we are on the cusp of something transformative.
I remain skeptical. I think we need to be wary of the hype and focus on building more robust, interpretable, and fundamentally sound AI systems. Otherwise, we're just creating very complex black boxes that we don't understand.
And black boxes that could perpetuate existing inequalities and biases. We need to be very careful about how we develop these technologies and ensure that they are aligned with human values.
Well, that's a sobering thought to end on. It seems we agree that while the idea of self-training in large reasoning models is promising, there are still many challenges and unanswered questions. We need to move beyond pattern matching, incorporate knowledge about the physical world, and ensure that these technologies are aligned with human values. A lot of work to be done. Thanks for joining me in the discussion. It's been really insightful.
My pleasure. Always stimulating.
Thank you. Good discussion.
It was great. Thanks.